righty. Well, let's get going with the introductory remarks here. Really excited about today's meetup. Our presenter is going to be Santosh GSK, and we're going to be talking about object detection, in particular, focusing on the YOLO9000 or the YOLO algorithm. But I think we'll get a broad sense of the object detection landscape along the way. So this is our general agenda for the session. I'll share a few words and then we'll dive into our community discussion. That is basically an opportunity for us to talk about, what we're working on, what we've seen over the past month or few weeks that caught our interest. We'll dive into our main presentation around a quarter after, and Santosh will basically close it out. I've got it here for half an hour pres and 15 minutes Q&A, but more often than not, you'll get questions and answers throughout the session, Santosh, so use the time accordingly.
Okay.
We've done a pretty good job of getting folks out on time, so should be good. A few words before we jump into discussion. There are a bunch of new faces on today, new names, and maybe some of you came via some of the discussion around the fast.ai or learned about the meetup via the fast.ai course. Basically, I did an interview. I'm actually going to mute everyone, but feel free to unmute yourself if you've got something to say when we get to the discussion part. We published an interview with Rachel, who's one of the founders of Fast AI. Fast AI offers courses on deep learning. And in that interview, I mentioned that doing this course, the Fast AI course, has been on my to-do list for a really long time, and I kind of threw down the gauntlet, said I was going to start at the beginning of June and invited folks to join in with me, and we've had a bunch of folks join the meetup interested in doing the Fast AI course with us. So if you are interested in following along and doing that course with us, the beginning Fast AI course is called Deep Learning for Coders. We're going to get started around the 1st or 4th of June. Just make sure to check into the Slack and find and add yourself to the Fast AI channel in Slack. Of course, we're always looking for presenters. If you're interested, we've got an application form over at TWiMLAI.com/meetupcfp. Check there. Our next couple of presentations are in June. Kelvin Ross will be presenting the paper cardiologist level arrhythmia detection with CNNs. And then Nick Teague will be walking us through a discussion around quantum computing and machine learning in July. Our speaker will take questions from time to time throughout the presentation. If you do have a question, feel free to just unmute and ask. If you prefer to submit your question via either the Zoom chat or the Meetup channel on Slack, feel free to do so. It's difficult for presenters to keep an eye on all these channels while they're presenting. So Santosh, don't worry about that. I'll follow the Q&A and I'll find a good time to interrupt you if someone has a question. All right, and so now is time for our community discussion segment. Feel free to chime in on any of these things. Questions or comments from recent interviews, topics or guests that you'd like to hear from, what you're up to, what papers or projects you've seen that have caught your interest, or what you're thinking. Anyone want to jump in and go first? I always feel like, oh, everyone's muted. So unmute yourself if you've got something to say.
Hey there, it's Nick. I was just going to share that I did another blog post that on kind of inspired by the show, actually, the differential privacy episodes. And I'll go ahead and post a link in the chat in case anyone's interested.
Awesome. What did you think about those episodes?
No, I thought they were well done. It sounded like it was really like cutting edge, like kind of. I kind of got the impression that it's a subject that needs to be talked about more. That isn't necessarily like like in all of the introductory courses that I've taken, it hasn't really been addressed. And I feel like it's something that should be.
Yeah, it's definitely emerging. Yeah, when we talk about ML and AI, like a lot of the things that we're doing now have been around for years, but have become recently popularized because we've got more compute, more data, all of that stuff. This stuff is all relatively new. So the differential privacy research thread, of course, there's been previous research into privacy and applying privacy to machine learning, but differential privacy is about 10 years old, as I understand it.
Cool.
It's a pretty interesting topic. So if anyone's on and hasn't had a chance to dig into that series, I definitely encourage it. Anyone else? Who saw the Google Duplex launch or the chatter about the Duplex launch? Anyone have any takes on that?
Yeah, I do. Go ahead.
Yeah, so I had a discussion with one of my friend, as in what is the stage where we call that this is crossing the border. We should not do anything on these lines where you are trying to mimic a human, where the other person might be fooled into assuming that this is a AI or this is a human. So what are the implications of trying to mimic a human and completely replace a human in a conversation? So in terms of ethical front, should we actually proceed in this direction is one thing that we were discussing. Of course, yeah, it's open for discussion. So.
Someone else?
I just heard some commentary on that. Apparently, Google are going to be identifying themselves as a Google bot when they do those sort of calls, which I think is a step in the right direction, right? So at least you know it's a bot that you're talking to.
Yeah, that came pretty quickly after the commotion, if you will, in response to the announcement. I've got mixed feelings about it. I think. Or I should say, I did not immediately react that it was this huge, deception or, mistrust. I think the research into making voices, computer generated voices, sound more natural. Like that's something that I think we've all wanted for a long time after listening to Siri and Google Home and Alexa, all these things. And it's interesting. We kind of, they got to the point where they're starting to kind of push the limit and to see how, I thought it was interesting just to see how folks reacted to it. I think it's, the other thing I was thinking about is that, in a lot of ways, like the bot now, it's kind of this bot human interface is like an API. It's just like a really horrible and inefficient API. And makes you wonder, if there's if maybe they or we invested collectively into getting businesses, online with real APIs, we can cut out some of this using bots as a kind of a cheap intermediary. But I don't know. I think it's an interesting. I definitely see the point and the concern, and I think if you kind of take it, further. The big thing that did worry me about that was less about the fact that, it could be done and that it's deceptive and more about kind of commercial abuse. So if you think about, when the cost of getting your attention via mail dropped from, sending a stamp to just getting spam, you had to deal with, until we figured out how to kind of filter all that stuff out, we had to deal with a ton of folks basically stealing our attention because it was cheap for them to do so. And, now with, there's a possibility of that happening via phones and via voice. Kind of interesting. Any other thoughts on that, or anything else that anyone wants to chime in on?
It's definitely a narrow domain of application, but given the success, that was demonstrated in the recordings that were released as part of the announcement, I'm kind of curious if anyone else thinks this qualifies as passing the Turing test. Is having a computer fool a human into thinking they're interacting with another human. And granted, they don't know they're taking the test, but it's still, to a degree, I'm convinced those people on the other end of the line, they thought they were talking to another person.
Anyone want to chime in on that?
Yeah, I think it's probably too narrow to consider it as passing the Turing test because it's such a narrow domain. But I agree, they thought they were talking to a person.
Yeah.
Yeah, I saw. Go ahead.
Yeah, I was wondering, as far as domain goes, I wonder how quickly this will expand on its capabilities. I think that they've proven themselves to be quite capable and probably will expand fairly quickly. So in other words, it's coming up, on the horizon very quickly, where AI will certainly pass the Turing test in a broad sense.
Yeah, I think, I guess my sense is that it is likely to jump from one domain to the next, like booking hair appointments to reserving restaurants to setting appointments for, getting your oil change or something like that. But it's still a long way from that to some general AI that can, fool you with any arbitrary question, fool you with you giving it any arbitrary question. Just my take. Anyone disagree with that?
There's one company, I forgot the name of it, but what they try to do is, using minimal data of a individual voice, they can actually mimic the exact voice, and they can build an agent which talks just like you, so that the other person can actually be fooled that this is this person. So there's a company which has been doing this since the last 3 to 4 years. I don't know the implications of that, but if these models are open sourced, and there are chances that people can do the same thing with any adversarial examples that we are seeing right now.
Yeah, I remember seeing that as well. And to that point, Samuel in the Zoom chat notes that essentially he thinks that the freak out over this is a little bit overblown, and that we have no problem with voice swapping, like you're saying, or swapping faces. Like, these are all things that are possible now, and you haven't seen quite the same level of commotion. Someone chimed in and said it's Lyrebird, Lyre Bird is the name of that company.
Yeah.
I think there's a paper from Baidu as well about the same, how they can basically clone your voice given a bunch of samples. That aside, I'd be curious, does anyone know how Google is achieving this? Like, what are all the systems working together to get what they're showing?
So the last time I checked, they were using the Tacoton 2 model, which is a text-to-speech model combined with WaveNet. They already had pretty good success in mimicking a human voice with the Tacoton model, and now they have improved with the new version as well. So that's what is used behind the Duplex, but I'm not really sure exactly how it is used along with the conversation in picture.
Right, but I'm curious on the jump that they're making. I mean, even if you use Google Assistant or a Google Home, like, a good percentage of time it's not able to get a natural conversation. So I'm curious on the jump that they made from a device like Google Home to Duplex.
Yeah, I think there's a bunch of elements to a natural conversation, and that we didn't necessarily see a natural conversation in that demo. We saw a demo. We saw something that we don't even really know how scripted it was, and how much variability on the part of the human that the Duplex was talking to would have been tolerable before it totally, went Alexa on us. Oh, I'm sorry, I don't know. I'm sorry, I don't know. So where out of time for the community discussion, and I don't want to cut too deeply into Santosh's time. We do have, or rather Google has published some information about what they've done on their research blog, and I'll dig into it as well and see if we can figure out, see if we can maybe get some conversations going on the podcast that get us closer to understanding how far they are along with this. But without any further ado, I want to turn over to Santosh to walk us through his presentation on object detection with YOLO.
Sure. So as you guys know, the topic for today is about discussing the YOLO version 2, which is also called YOLO9000. And the agenda of this talk is to have a little introduction to what object detection is. And then we walk through the history of deep learning algorithms that were used to solve the problem of object detection. And then we'll be going in depth of how the YOLO v2 algorithm is built in and how we can train it using something called a cyclic learning rates. This is not mentioned in the original paper, but I've tried implementing this cyclic learning rates, having learned from fast.ai, and they turned out to be pretty well in terms of improving the accuracies in lesser iterations. So we can also go through the paper as well. And after that, I'll do a small walkthrough of the code that I have written for this. And you guys also can refer to that if you are interested in implementing it by yourself. And then we'll have a small discussion on what happened in the recent past, what are the limitations of YOLO v2, and what has been done in the recent past regarding that. So object detection is nothing but identifying all objects and trying to find the bounding boxes for each of those objects in an image. So in short, each bounding box would need a class label along with the position of the box, which can be determined by 4 factors: the XY position and the width and height of the box. And the earliest approaches that try to solve object detection is region-based CNN. So the author of region-based CNN was inspired by AlexNet and thought, why can't we use deep learning to solve object detection? So they had a very naive approach. All they wanted to do was to use AlexNet to improve the object detection. So this approach was like they used something called a selective search to come up with the proposals of regions. What do I mean by that? To give an example, let's look at this input image here. You see all the yellow boxes here. So in order to identify what are the probable objects, they use something called a selective search. It is nothing but a simple computer vision based algorithm which looks at pixel colors and pixel textures and groups the pixels based on some hierarchical clustering algorithm and tells that these are the proposal objects that might be of interest to you. So they get 2000 of such proposals from selective search, and then they use AlexNet on top of each of these proposals. They do a forward pass on each of these proposals to get the CNN features. Once they get the CNN features, they use an SVM algorithm to predict the class of each of the proposals. So it's a very broken approach in terms of they use multiple algorithms to complete one task. And at the final stage, they want to find the coordinates of the bounding box. To do that, they use simple linear regression. So obviously, this would take a lot of time as it involves a lot of steps. So the authors thought that we have to reduce the number of steps involved, and they thought of coming up with one architecture to do the entire classification and regression task of the bounding box. So then they came up with this approach called fast RCNN, where the first step was to again use the selective search as a proposal method to identify the regions of interest. Once they find the regions of interest, they do a single forward pass of pre-trained AlexNet. So earlier they were doing a forward pass for each of those regions of interest, which was too costly for them. Now they did a single forward pass. After they do the single forward pass, they have built a network which is consisting of fully connected layers like here, And using these layers, they are able to predict the class probabilities along with the bounding box regressors. What do I mean by bounding box regressors is nothing but the XY positions and the height and width of each of the bounding boxes. So fast RCNN was able to improve the computational cost, but there's nothing on terms of the accuracy of the algorithm. So later they actually looking at, improving the algorithm further, and they saw selective search itself is a bottleneck in terms of improving the speed of the algorithm. So then they came up with this approach, faster RCNN, and what they implemented here is a regional proposal network. A regional proposal network simply replaces the selective search algorithm using a convolutional neural network, and the rest of the process is very similar to fast RCNN. Once you get the regions out of this regional proposal network, you give that to the fast RCNN to get your bounding box predictions. So how does a regional proposal network looks like is, given an input image, you pass it through convolution layers. It can be your VGG, it can be a ResNet, whatever. You pass it through convolution layers and you get your feature maps. Once these feature maps are generated, you give it your regional proposal network. A regional proposal network is nothing but a simple convolution network where if you think of a convolution network as 3x3 kernel, at each kernel, you're trying to generate 5 or 10 anchor boxes. What do I mean by anchor box? The one that you see here, different rectangle boxes of different aspect ratios. So like in an image, if you want to find an object, you usually come up with a prior set of anchor boxes. By anchor boxes, what I mean is, in this image, you are seeing the yellow boxes, right? These are a set of anchor boxes that can be possibly contain object. So it can be a rectangle with a larger width, or it can be a rectangle with a larger height. So these are what we observe in usual images. So these people have come up with 9 such anchor boxes, which are predetermined by human labelings. And for each of the kernel, they were telling that whether there is an object in that kernel of the feature map. So what do I mean by that? Here, if you look at the convolution layers, it outputs your feature map. On this feature map, you are running the 3x3 kernel. So let's say on the very top left, you have a 3x3 kernel, and that kernel will actually generate 9 anchor boxes. And it gives you a prediction saying that whether this 9 anchor boxes, each of them, does it have an object or not. At the end of this process, you have come up with 3 region proposals, where it means that these three anchor boxes might contain an object. So these 3 anchor boxes, along with the feature maps, are used by this faster RCNN to predict what is your object classification and the bounding box predictions. So am I going too fast, or is it clear?
Anyone have any questions?
Okay. So these are the one of the earliest techniques that are used to find the object detections. Later, one of the most talked about algorithm is the single shot detector, which is very competitive with YOLO as well. So what single shot detector does is, it doesn't have the selective search process. All it does is a fully convolutional network. Here you see like SSD starts with an image of 300 by 300 with the channels of 3. You pass that image to a VGG network of 16 layers, your simple straightforward VGG network. After your VGG network, here it has a multiple convolution layers with a decreasing width of your feature maps. This looks like a pyramid. If you think of it, you have a bigger convolution layer, and then it just goes on top with a smaller width. So it looks like a pyramid, right? And instead of just looking at the end convolution feature map, so what they're trying to do is, the most of the fast RCN and faster RCN, they look at the end convolutional feature map. From there, they try to predict the anchor boxes or your bounding boxes. Instead of that, they looked at multiple previous convolutional feature maps. They said that, hey, why don't we look at the layer before that, or the layer before the previous layer, to generate our anchor boxes. So to give an example, if you look at the very top line, it says classifier convolution 3x3, 4 into classes plus 4. What does it say is that it is looking at a convolution layer in the VGG network, and from there it is generating 4 anchor boxes with a 3x3 kernel. So here 3x3 means a 3x3 kernel. For each kernel, it is generating 4 anchor boxes, and each anchor box that has a probability of belonging to each of your class, along with 4 values for predicting the position of your anchor box. That is the very top line here. Below extra feature layers, you can see classifier convolution. So
Santosh, Harsha asks in the Zoom chat, what is the VGG network and what's its role?
Okay, so VGG is a convolutional network which was used previously to predict the ImageNet classification problem. It was able to successfully give better results on ImageNet classifications, the 1000 classes problem. And from there on, VGG16 is a traditionally heavily used network in most of the other deep learning architectures, only because this network can capture the real world patterns from images. So VGG16 is a network which contains 16 layers of convolutions, and it was run on ImageNet 1000 dataset, 1000 class dataset, and it got some good accuracy up to 93% top 5 accuracy. From there on, people are using that same pre-trained network in solving all your classification tasks, because these images that go into SSD or YOLO or any of your image segmentation problem are real world images. They mimic what the images are in ImageNet competition as well. So VGG, which was trained on ImageNet, can also give you a good representation on your problems in SSD, in your object detection. So that's why we use VGG to give you a good natural representation of images. And from there on, you are able to implement any of your favorite algorithms.
So you can kind of look at this diagram as saying that first layer, that VGG network, is trying to identify, if and where there are objects within the image. And then the rest of the network is more generally trying to kind of localize them and identify and kind of figure out the bounding boxes.
Right. So the output of VGG would be like, if you have a cat in an image, it will be able to identify the boundary of its face, or maybe it will be able to identify the eyes of the cat. It will be, the VGG can represent the real world images. Instead of, let's say, using a new network altogether, you can use VGG so that you already have the weights pre-trained from an ImageNet dataset, which is much huge than any of your object detection datasets. So at the end of this VGG, you have a pattern representation of your real world image, of your input image. Now you have the patterns represented. You can build further convolution layers, which can now try to predict the objects from the patterns. So first you have to represent the real world into computer vision patterns. So that is done by VGG here. It's a simple convolution network.
Great, thank you. So there's another question from Evaliv in the Zoom chat. And I think he's asking where the classes plus 4 come from. Is that the two, the 2 of that 4 is from the XY and then 2 with height, or is it something else?
Yeah, exactly. That's right. That's right, Sam. 4 is the value XY, width and height for each of the bounding box. So if you want to predict a bounding box, you have to know what is the location and what is the width and height of the bounding box. That's why you have 4 there. And you want to know what class does that bounding box belongs to. So you have the classes as well. So for each bounding box, you need the number of classes, the probability of each class, plus 4 values for the position of the bounding box.
Great.
So yeah. So at the end of this network, you have all your feature maps, all your bounding boxes combined, and then you have around 8,000 of them bounding boxes at the end of this network. But you don't have 8,000 objects in an image, right? You just have 1 or 2 or maybe 4. So from those 8,000, you need to identify those 2 or 3 objects in the image. For that, they use something called as a non-max suppression, which I'm going to discuss later in the slides. So once you have all these bounding box predictions, we have techniques to reduce those predictions into 1 or 2 predictions that can relate to an object in the image. So
okay, one more question before you leave that slide. Nick is asking that he generally thought that in CNNs, you're generally increasing the number of feature detectors with the layers. But in this diagram, we're decreasing the number of feature detectors with the layers.
Right.
Is that unusual or no big deal here?
So here as well, what they're trying to do is they're actually increasing the feature detectors 1024 in the first layer, and then they are increasing the number of convolution layers but decreasing the number of filters. So that's pretty normal, I believe. And whenever you come to the end, you usually look at classification problems where you see number of feature layers are increasing at the very end, but it changes with every problem. And yeah, this is not unusual as well. However, the major caveat is that they are using convolution layers at different aspect ratios, like not just from the very end convolution feature maps, they're also using convolutions from the layer before that and from the layer before that. All these lines you see here, so they're using all of them together, and that negates the loss of information of in having reduced feature maps towards the end. Is that clear?
Yep.
Okay. So coming to YOLO v2, the primary idea of YOLO v2 is that for any given image, we break down into an n by n grids. Here for this example, I took 13 by 13. So each of this is called as a grid cell. And for each grid cell, the YOLO v2 predicts 5 anchor boxes. So this is what anchor box looks like. And for this, I guess it's like 1, 2, 3, 4, 5, 6, 7, 8, 9th row and 4, 5, 6, 7th column. So for the 9th row and 7th column grid cell, we are predicting 5 anchor boxes with different aspect ratios. And for each of those anchor box, the YOLO predicts the coordinates within the square, the width and height of the box with respect to the image width, and the confidence score of having any object in that box. So unlike SSD or unlike FASTER, here YOLO predicts a confidence score irrespective of the class. It just predicts if there is an object in this anchor box or not. Along with that, it also predicts probabilities of belonging to each of the M classes. So in total, each bounding box would have 5 plus M predictions, where 5 being the coordinates are 2, the width and height are 2, and the confidence score, plus 5 prediction, M prediction for the classes. So each bounding box would have 5 plus M, and each grid would have 5 anchor boxes. So we have a total of 5 into 5 plus M predictions per grid cell. Once we have these predictions, now the task is to reduce these anchor boxes to find the object. How do we do that? There are 2 steps. The first is to remove those anchor boxes which contain no object. Here we can simply look at the confidence score. If it is less than 0.24, which is mentioned in this YOLO implementation, but it's up to you. If it is less than 0.24, you just ignore that anchor box. You suppress that anchor box. And for the remaining anchor boxes, you use something called as intersection over union and non-max suppression. I'm going to explain them, what they are. So intersection over union is nothing but, let's say there are two bounding boxes in an image. You look at what is the area that is intersected by these two boxes, divided by that, what is the total area of these two bounding boxes. It just gives you an idea of how overlapping these two bounding boxes are. That is IOU. And non-max suppression is nothing but, let's say in this example, we have multiple bounding boxes trying to identify the same object, which is redundant. We don't want to do that. We just want to have one bounding box. So we use something called as non-max suppression algorithm to go from this picture where we have multiple bounding boxes to come to this picture where we have just one bounding box per object. And the algorithm to do that is that, let's say in this example, we have only one class, which is person. We find all the bounding boxes that identify a person in those boxes. Now, once we get the highest confident bounding box. So in this, we have like 4 bounding boxes. We get the one which has the highest confidence, and we pick this green one, which has the highest confidence. We suppress the rest of the bounding boxes, which has an overlap with the selected bounding box. And overlap can be defined by IOU. If a bounding box has an overlap of greater than 0.3 IOU, we suppress that bounding box because we already identified an object in the similar space. And we just repeat this process if there are any bounding boxes left. That is the non-max suppression. If there are any doubts, I can take it here.
Any questions on this?
Okay. So I just need to take you to the visualization of YOLO V2 network. Can you see the screen?
We still see the slides right now.
Okay. Let me share. Yeah. Can you see the network now?
Yep.
Yeah.
Sure. So this is a YOLO V2 network. It is very similar to other like convolution networks. You have a convolution layer followed by max pool. You can again have a convolution followed by max pool. Every convolution has a batch norm, and the activation is leaky ReLU. This is a very straightforward network, but what I want you to observe here is that after convolution layer 13, which has filters of 5 and 2, we have a branch which is going to a reorganization layer. I'm going to explain what a reorganization layer is. This reorganization layer, the output of reorganization layer is concatenated with convolution 20 layer. This is what YOLO has come up with. This is the insight of YOLO. And this concat layer goes through again a couple of convolution layers. And then there is a regional layer. Region is not a layer, it's just a post-processing of your output. I'm going to explain that as well. So all I want you to focus is on that. After convolution layer 13, we are going through a reorganization layer. And there's another arm which goes to max pool and a couple of convolution layers. And then we are concatenating the results. So, yeah. So what the reorganization layer does is that, let's say we have a convolution feature map of size 4 by 4. It takes the alternating pixels and puts that into a different channel. So here, if you see the example of 1, 2, 3, 4 up to 16, what it does is that it created 4 channels out of this one channel, and each channel would have alternating pixels. 1, 3, 9, 11 is alternating, 2, 4, 10, 12. So what they try to do here is that they try to get the feature maps from higher dimensions, and then use that in your lower dimensions to make up for your loss of information. So that's what reorganization layer tries to do. It just reduces the size into half and increases your number of channels by 4x. Now the concat layer, all it does is just concats both the output in the channel dimension. So you have your convolution 20, which has a dimension of 1024 by 13 by 13. Don't worry about it. So I just want to give an example of what happens in concat layer. From the reorganization layer, we got the output as 2048 into 13 by 13. By concatenating both of them, we get the output to be 3072, which is just addition of the channels here. So that's what concat does. As we are training on Pascal Vogue dataset, we have 20 classes in the dataset. And as I was mentioning earlier, the number of predictions per cell is 5 into 5 plus m, where m is 20 for Pascal. So we have 125 predictions per grid cell. So that's what the output of your YOLO will be, 125 into 13 by 13. 13 by 13 is a grid cell size. So what is the region layer does? What is the post-processing that happens after the last layer is that once we have the predictions for each anchor box.
Can I jump in with a question? Sure. The reorganization layer, is there some intuition for, what the skipping pixels does here? Is it like compressing the features, or is there some intuition for us there?
So I thought about it, but I couldn't come up with anything. The best thing that I could come up with, maybe they did something else, max pooling. Maybe what max pooling does is something similar, but I couldn't come up with an intuition here.
Someone suggests black magic might be the answer.
Yeah, until it works, it's always worth it to read.
The famed graduate student descent. Okay.
Yeah. So the post-processing is very simple. All we have is simple predictions from the convolution layer. It can be a -3, it can be +5. The values can range from anywhere to anywhere. But all we need is we want to predict the location of the bonding box within the grid cell. By that, we want to restrict it to from 0 to 1. So we just do a little post-processing. We just apply a sigmoid function on the XY coordinates of the bonding box, which gives us the value from 0 to 1. And we add it to the offset of the grid. In the example that I shown you earlier, here the offset is like 9,7 for this particular grid that we add it to the predictions given by the YOLO network. That is the TX and TY are the predictions here. Similarly, for the width and height, the predictions are TW and TH, let's say. We multiply that, we do a e power the values, and then we multiply with the prior width and height of the anchor box. To mention about the prior width and height, what do I mean by PWPH is that the authors have come up with what are the probable anchor boxes that can explain most of the objects in my data set. So what should be the aspect ratio? Should it be 1:1? Should it be 2:1? Or should it be 3:1? So they came up with this prior information by applying clustering on top of the training data. All the bonding boxes, they can get it from the training data. They applied clustering and found out that, hey, these 5 priors can explain most of my objects, and let's use them in building this detection. So that's a very interesting take, because most of the earlier approaches like faster RCNN or SSD, they just came up with some manual priors, which obviously were inefficient, which are not data driven. So YOLO had this very good idea that from the training data, they generated the priors for the anchor boxes. And for the remaining class probabilities, which are from T1 to T20, they simply did a softmax transformation to get your probabilities.
So there's a question here about elaborating on the BX and BY.
Okay.
At maximum bx equals 1 plus cx, is that supposed to be the right side of the grid? Y1 plus, is there scaling happening here? Does that question make sense?
Right. So as I was mentioning, cx and cy is a offset of the grid. So in the example, cx is 9. Here in this example, cx is 9 and cy is 6, I guess. And the predictions, whatever we get from the YOLO, we round it off from 0 to 1. And that way we can actually make sure our bounding box coordinates fall within the grid cell. It doesn't fall outside the grid cell. So the sigmoid plus cx, make sure that you have your bounding box centered somewhere in the grid cell.
Okay, so the bx by aren't coordinates. They're meant to be within a given grid cell as opposed to somewhere else in the image.
Yes. Yeah. So if you're predicting for the grid cell, the bx and by should be having those values within the grid cell. Which was not the case with other algorithms. They were just coming up with tx plus cy, where tx plus cx, where the bx values are just going off the grid cell values, so which was inefficient. And this is a good addition here.
Got it.
Okay. And now the loss function. It looks scary maybe, but it's very simple. All it tries to do is that if you look at, again, I go to the example. If you look at this, there are multiple bounding boxes over entire image, and most of the bounding boxes doesn't contain an object. So what we need to do is we have to reduce the confidence score of those bounding boxes where there are no images, right? Where there are no objects.
No
right?
objects.
Yeah, that is our first term in the loss function, which is if our max IOU is less than threshold, if our bounding boxes doesn't contain any ground truth, we reduce the objectness score of that. That is our first loss function. And the second thing is that all those bounding box width or height or positions need to match with the prior information. The prior information, by that I mean the prior width and height that the authors have calculated from the training data. So let's say if the ratio is 1:2, the predictions should actually follow that 1:2 ratio. For that, they made another term for at least 12,800 iterations. We have to make sure that the predictions align with the prior information of the anchor boxes. So that's why they have the second loss term. And finally, if your bounding box contains the truth, if it contains an object, we have to look at the predictions in terms of the coordinates. It should match with the truth labels, truth box, and also the objectness score. You have to improve your objectness score, and also you have to reduce your classification error. So that is our third loss term, which is if your bounding box K contains a truth, which is denoted by IK truth, you have to reduce all these three terms. And we can discuss it here itself. One thing that is lacking in this loss function is that if you have a very large object, you can be okay with any localization errors. By localization, I mean if the bounding box is little off from the truth object, that should be fine with you. But if the size of the object is very small, then you should have a very stringent loss saying that, hey, I don't want any error on the bounding box coordinates if the size of the object is too small. That is something missing in this. And that's what happened to be a drawback of YOLO. Am I clear? Any questions?
Any questions on this one?
Because it's very hard to actually find the loss function. Most of the papers, they don't write the right loss function. And most of the implementations out there, which says, YOLO in PyTorch or YOLO in TensorFlow, they write a different loss function altogether. I found it very difficult to use any open source because most of them don't follow the paper's implementation. So I went to the implementation of the author. I went through his code and found that hey, this is the loss function no one has written about, and no open source code has done it in the way it has done. So
interesting. Yeah, I'm flipping through the paper trying to find the loss function in the paper, and it's not here.
They didn't mention that. Yeah, it was in the first version of YOLO, and they didn't follow that in their implementation as well.
Okay.
So yeah, it happens all the time in papers. So having said the loss function, now coming to the training. Before I mentioned the training, they proposed something called as .NET 19. The architecture name, they just came up with the name .NET 19. There is nothing but they have 19 convolutional networks here, which is we can see on the right side. It's just a combination of convolutional and max pool. And this network is pre-trained on ImageNet 1000 again, just like VGG. They're doing the same thing. They're replacing the VGG with .NET 19. There's a good reason for that. I'll tell you about that. And once they have trained .NET 19 on ImageNet for a good number of epochs, they use these weights in training the YOLO v2. That's how most of the algorithms also work. So the reason behind the using .NET 19 instead of VGG 16 is that the number of floating point operations that happen in VGG 16 are way higher than .NET 19. This helps in reducing the computation cost while you're doing an inference. This would help you, give a more real-time speed of object detection. That's the crucial addition of YOLO v2 again, where they came up with their own architecture. Most of the SSD, they use VG16, others also use VG16, but these guys came up with their own architecture inspired from GoogleNet, and they're able to have very high speed object detection because of this network. So if you see .NET 19 has very high similarity with YOLO v2 network, which I showed earlier. The top 19 layers are exactly the same as YOLO v2. Hence, after training the .NET 19 on ImageNet, we use the layers up to the top 19 layers. The same weights will be used in YOLO v2 network as well. So YOLO v2 network obviously doesn't have the last average pooling on softmax and 1000 filter convolutions. Those are removed from YOLO v2 and a few layers are added. Those layers will be learned in our next step. So now we have the pre-trained weights. All we need to do is learn those extra layers that are added in the YOLO v2. So I tried several approaches mentioned in the paper. I iterated on several learning rates, but then I came across this cyclic learning rates, which was mentioned in Fast AI lectures, which was wonderful, and you should also check it out if you haven't already. What they tell is that fixing a learning rate is one of the toughest problems in training a deep learning model, because if you fix it too low, you might end up forever in training your algorithm, or if you fix it too high, you might jump across and never reach a local minima. So it's very, very crucial in identifying the right learning rate. So in a paper by Leslie Smith called Cyclic Learning Rates for Training Neural Networks, one approach they suggested is that with every iteration, linearly or exponentially increase your learning rate until you see that your loss is increasing. So if you can see in the example here, from 10 power minus 5, we exponentially increased our learning rate, and we see that at around 10 power in learning rate at 1, we see loss is increasing, and that's when we stop. And that's when we stop and come back and visualize this graph and see, hey, at 10 power minus 1, my loss has started to increase where I want it to decrease. So I don't look at 10 power minus 1, I just go a step before. I look at 10 power minus 2 and see that there's a huge curve in the downward direction. That means there is a great deal of learning that is happening at 10 power minus 2 learning rate. So that's where I want to start my network. I want to start my learning. temper -2. That's the key insight from this paper, is identifying your learning rate before you even start your training. So once you identified it, there was another paper, stochastic gradient descents with warm restarts. What they tell is that if you, let's say, start with temper -2, you don't have to stick with temper -2 for the rest of your training process. You have to decrease your learning rate with every iteration. The way you decrease can be different. Here, they have used a cosine annealing. You can still go for a linear decrease or any other way. After you decrease your learning rate, and if it reaches 0, you can restart to the point where you started off, which is temper -2 in our case. So why does, this is proposed? Why do they even say that, hey, you should follow this? The reason is very simple. In most of the deep learning algorithms, the reason we stuck is not because of a local minima, but because of something called as saddle point, where the derivatives of 0, but you haven't reached the local minima here in all directions. In the direction of A to B, you reach the minima, but in the direction of C to D, you are not there at the minimum position. What happens in saddle point is that the algorithm tells the learning is done. I'm not able to learn anything further, and you reach a suboptimal solution. To escape such saddle points, whenever you do a restart, your algorithm pushes your point from the saddle point to a different point altogether, and hopefully you reach in a much better local minima. That's the main idea behind stochastic gradient descents with restarts. And I just followed this approach, and I was able to get good results here. So I started with the LR find, the learning rate find algorithm, and found out to be around 0.00025. I implemented it in PyTorch, and then I already had the pre-training weights, right? So all I need to do is train the last layers which I've added for YOLO v2. For that, I did 5 cycles, where with each cycle I doubled my learning rate, the decrease in learning rate, just like in this example here. In the right side graph, we are decreasing the learning rate in a slower manner with every iteration. I did that for 5 cycles, and later I did something called as a differential learning rate. So most often what we hear is that in transfer learning, we have, let's say, 20 layers pre-trained on ImageNet, and then we add 2 layers at the top, at the bottom, and then just train those 2 layers and you're done. But we never train those early 20 layers, even if we train the 2 layers to the full extent. So what happens is that for your own problem, maybe you need to retrain those 20 layers even for a small extent, so that your weights are a little bit tuned towards your problem statement. So what differential learning rate tells is that, hey, the pre-trained weights which you are used are very good, but you have to retrain them with a very small learning rate for, let's say, 2 cycles or 3 cycles, which will help you improve your accuracies. So that's what differential learning rate does, and I've done that, and I was able to get an MAP of mean average precision of 71.8 on the Pascal Walk 2007. So Pascal has 2 data sets, 2007 and 2012. So most of the papers, they train on 2012 train and test, 2007 train combined, and they test on 2007 test data set. So with this, I was able to achieve 71.8, but using the approach mentioned in the paper, I was able to get around 68.2 MAP. So cyclic learning rates turns out to be a very good addition to the way we train our networks. And yeah, that's how I trained it. Any questions?
So we're at the top of the hour. Are you close to your summary?
Yes, I'm close to my summary.
Okay.
Yeah, so some of the challenges are that YOLO struggles with objects in small sizes, like flock of birds, or if you have satellite images and trying to count the number of boats in a scene. YOLO couldn't able to do that because most of the times, it just doesn't use most of the previous convolution layers. So that is one of the drawback, and also the localization errors, as I mentioned earlier. The small objects and the large objects are given an equal weightage in terms of the bounding box error that comes in. And in order to address that, YOLO has come up with a new version just a couple of months ago, in March, I guess. And in this version, they're trying to address few of these issues by upscaling of convolution features and also using feature maps at different scales. It's a very easy to go through paper, and I guess everyone can also try that, because as of today, the state of the art is YOLO v2, and they have improved YOLO v2 further, and it's what they try to see how much we can achieve that.
And that one's also a very funny paper. It's probably the funniest paper you'll ever read.
I can't think of any other paper which is as funny as it.
Awesome.
Okay.
Cool. So you're done?
Yeah.
Any final questions before we wrap up? The funny paper was the YOLO v3 paper. You just Google YOLO v3, you'll find it. Santosh, do you have a link to a GitHub with code in it?
Sure, I'll add in the chat.
Okay. And your slides as well. If you send me your slides, I'll get them posted on the Slack. And the recording will be posted shortly up on the Meetup page.
Sure. Okay.
And Swix dropped a link to the YOLO v3 paper in the Zoom chat. So you mentioned that several times that you mentioned the Fast AI course several times in the context of this discussion. Did you take that one? Did you do that one recently?
I did it in around January.
Okay.
The 2018 V1.
And would you say that if folks were, didn't fully understand this, your presentation, that after taking that course that they would more thoroughly understand it?
Yeah, definitely. I mean, Jeremy had done a great job in explaining that. I was able to easily understand it and implement it right away. So I'm pretty sure everyone will be able to do that as well.
Awesome. So the timing is really good then for us to jump into this Fast AI course. If anyone wants to join in, again, find the Fast AI channel in Slack, and we'll figure out what exactly a study and support group means for this. But we'll just kind of encourage each other and have another place to get questions answered. There's also the Fast AI forums as well. But yeah, a bunch of people have expressed interest. So if you're interested, let us know. And Santosh, thanks so much. That was a great presentation.
Thank you. Thank you for your time.
Yeah, thank you very much.
Awesome. Well, thanks everyone. Great to see everyone, and looking forward to next time. We will definitely keep you posted, and you'll be able to find, once again, the recording on the meetup page at TWiMLAI.com/meetup. Take care and good night or morning, wherever you are.
Thank you. Have a good night.
Bye-bye.
Good night.
Thanks.
Thanks.